Greetings from Below Brain Gains channel. I'm Mark Tomerdahl, and I'm going to talk a little bit about aging and brain health in this chat. And let's go ahead and start showing what we have here. And basically, the keywords on this are aging, plasticity, and brain health. And even though the brain gauge has only been around for 5-6 years, the prototypes of the brain gauge go way back. And we were using a prototype of the brain gauge back in 2006, and we reported this data in 2007, and we did our own aging study. And so we're going to talk about those results now. And the whole point of this is that we're using stimuli through the sense of touch to probe brain function. And we want to see what brain functions change with age and what do not. And do brain change, if you keep healthy, does your brain change? That's the main question that we want to ask. So let's see what does change with age. And the first metrics that we looked at here were basically the same metric that everyone in the world had been looking at, which is threshold. And the static threshold is what we call sensory thresholds, are very similar to what people have been looking at. Static threshold is a minimum stimulus you can feel. In other words, think about like an eye chart. What's the smallest letter you can see? Or, what's the lightest touch you can feel? And that sense right here is bottom left-hand corner. That stimulus looks like this if you look at it on an oscilloscope. But basically what we're doing is we're vibrating the skin, and we give a stimulus, and we say, okay, and we basically track people to see what they can feel and what they can't feel. And what they can feel, you can actually measure that. And it starts out around 5 microns below the age of 25, and it goes up to around 10, 12, 15 microns by the time you're over 60. But that is just really related to skin sensitivity. So as thresholds go up, skin sensitivity is going down. You become less and less sensitive. Now, with the prototype of the brain gauge, we introduced a new measure that we call dynamic threshold. And dynamic threshold, again, it also goes up with age, but it's a little different in that instead of just delivering a stimulus that looks like this, we deliver a stimulus that looks like this. It's very, very small. It's sub-threshold. It's the tiniest stimulus ever. And it starts out almost at 0, and it gets bigger and bigger and bigger. And then what we are looking for is, when do you detect that stimulus? And generally, you detect that stimulus at a much larger size than the static threshold generates. And so and even though it's going up with age, that difference between these thresholds is relatively consistent. And basically, this is due to a feature that we call feed-forward inhibition. I'm not going to go into all the details now, but we've looked at it both in animal studies, and we've looked at it in other neurological populations, for instance, like in autism and chronic pain and diabetics. And so those are some interesting studies that you can read about or listen to talk about a dedicated feed-forward inhibition talk later. But that is a central mechanism. The feed-forward inhibition is a central mechanism. And you notice that that's not really changing as age gets, as your skin sensitivity is getting worse, and feeling less and less, but your brain is basically maintaining that difference. All right. So what else changes? Reaction time also changes. And, I'll give a plug for, there's a lot of reaction time studies out there. We've done some, and there's a lot on reaction time accuracy, which is really important to read about. But one thing that you'll find in the literature over and over and over again is you'll see that people say reaction time goes up with age. In other words, you get slower with age. And is that a central mechanism or not? And so obviously, it has a lot to do with centrally mediated function, and its reaction time is a very simple test. You deliver a stimulus, and then to the finger, or the finger receives the stimulus on the brain gauge, and then the subject responds as fast as they can. And that reaction time actually impacts the speed score on the brain gauge. And the speed, again, is just one of many of the metrics that we take. But choice reaction time is a little more complicated, but you also see that it's basically just shifts this whole trajectory up. And that's because a decision process is added to the simple reaction time, because one of two fingers is stimulated, and the decision about which stimulus or which finger received the stimulus has to be invoked and has to be taken into account to add, a significant amount of time. 150 to 200 milliseconds usually is what people add. So one of the things that we did, I mentioned that we screen people very carefully for neurological health, but you make mistakes, and this goes up a little bit, but again, there are a lot of papers that show that trajectory even higher, that people get even slower with age, except you do a little digging in the literature and you'll find that maybe this has not all got to do with it's got to do a little bit with brain health when it shifts up, and how carefully people are screening. As we get older and older, a larger percent of the population has something wrong with them, or has had something wrong with them. They've had multiple concussions, they've had chronic pain, or they have chronic pain, or they have some neurological disorder, or some neurological insult, or early Alzheimer's, but they're not screened out. And if you're not careful to screen those out, then these numbers can get really, really high. The other artifact is that if people are using really bad methods, if they're not using the brain gauge, if they're using something else, just using a simple computer program, you can add a couple hundred milliseconds to this entire trajectory, and everything will shift up all on its own. So anyway, that's a whole nother topic, and I encourage you to listen to reaction time accuracy talk. So what does correct for that? And then if you go through the literature, you can find really quickly, you can go back 1970s, you can find that there's a huge difference between active and inactive populations. We did not take that into account in our first paper. So, but if you correct for physical activity, you find that if you compare active versus inactive population, if you break up your healthy controls into active versus inactive, you find that the active participants were 10% faster in that early 20 to 30-year-old group back over here. Now, if you look at activity in 50 to 70-year-olds, you find that active versus inactive 50, 70-year-olds shows that people who are active are as much as 40% faster. So that could account for that trajectory, completely for that trajectory. So keeping neurological health, not just brain health in check, but overall physical health and staying physically active will bring that reaction time right back down. And basically the reaction time in some of these papers back in the 1970s showed that active older 50 to 70-year-olds actually outperform inactive 20 to 30-year-olds. So activity obviously has a lot to do with brain health. Activity is very important for brain health. So what measures did not change in our study? Well, the metrics, this looks at, if you're familiar with the brain gauge, this is an amplitude discrimination versus single site adaptation. And let's do amplitude discrimination. Amplitude discrimination is where we deliver two stimuli at the same time and just ask the subject how well he can tell the difference from them in terms of intensity. So which one is bigger is basically the question that's asked. And you can see that these numbers don't change a whole lot. And keep in mind, smaller numbers are better for this measure. And that all fits into this accuracy score for an individual. And let's just look at this part of the score. Basically, we're delivering a small stimulus and a large stimulus, and we're asking, which of these two is larger. Now, single site adaptation, what happens there? Well, what we do is we deliver a conditioning stimulus, which makes this stimulus feel smaller. If this larger stimulus feels smaller, then you're going to have a harder time telling the difference between those two, as long as all the circuitry is in place. And look at that. This difference, not just amplitude discrimination is constant, which leads to a constant accuracy score or healthy aging, but this difference between amplitude discrimination and single-site adaptation remains the same. Again, and that feeds into your plasticity score. But that tells you, okay, look at the difference here. It's very constant. This is how much worse people got with at amplitude discrimination when they received a conditioning stimulus. And we've done a lot of studies with this particular measure, and we find that with neurological insult or neurological disorders, that number, this number actually gets, this difference gets a lot smaller and sometimes disappears. In other words, this is an illusion, and that illusion is, basically your brain connects the dots in an illusion. And so this is functional adaptation. The brain is being conditioned by this first stimulus so that it kind of ignores a little bit of this stimulus. So anyway, that was a measure that we presented in this paper and showed that it stayed fairly constant with healthy aging. So a lot of measures stay constant with healthy aging, and you just need to know which ones to look at. And stay away from the traditional sensory testing measures of threshold testing. That's really not the best way to look at healthy aging. You want to look at super threshold measures such as accuracy and plasticity and even and reaction time for that matter. Those should, and focus. Those all should stay fairly constant. So anyway, other related videos, you may want to look at reaction time accuracy, feed-forward inhibition, or the amplitude and discrimination videos available on the Brain Gauge channel. So anyway, if you have any questions, make sure and send them to me, and I would be more than happy to make another video. Or if you tell me this one stunk, then I'll remake this one. Thanks for watching.